Stop right there. Yes, this is another video about detection. This one's fairly long. It's in 3 parts. I'll talk about infrared detectors as momentary contact sensors versus occupancy sensors, how they communicate with Digitrax LocoNet, and how LocoNet tells your software, in my case TrainController Bronze, to use that infrared detector data to make your trains stop at more precise points. Here's a disclaimer. I'm not an electrical engineer or an authorized Digitrax reseller or expert of the authoritative rank. If this is too basic, sorry for wasting your time. If I've got errors here, please straighten me out in the comments. I will not take offense, but I will try to revise this presentation. My North Penn branch layout has several stub terminals. It also has a 4-track staging yard. Each of the staging tracks has 2 consecutive blocks, so each staging track could hold 2 trains of about 8 to 10 cars each, one in front of the other. I want to run my trains automatically and then stop them at certain points, exact points in certain blocks. Now, there are several software packages out there that can run your trains automatically. Freiwald software offers Railroad & Co. TrainController in 3 versions: Bronze, Silver, and Gold. Bronze is simple to set up, and I have used it and been using it for over 10 years. But there's a big downside to TrainController, which may be a showstopper for you. I suspect that Freiwald is one-man operation, and Mr. Freiwald wants to retire, so he will stop selling his software as of June 30th, 2026. Existing licenses are perpetual and can be retained, but I'm sure, as you will guess, there is probably no further support. If you decide you want it, or to buy it or upgrade to version 11 now, do that, because the older versions require access from your PC to Freiwald servers to validate your license every time you open the software. Although Freiwald's website says those servers will remain live, I'm skeptical, and if they don't, your software will stop working. But unfortunately, Mr. Freiwald appears to be somewhat political and will not sell directly to U.S. customers. There are resellers who will apparently do so, which you can find by digging around on the Freiwald website. I'll list them in the description. The Swiss one looks viable, and I just ordered the upgrade to version 11. We'll see how that works. Other options are out there, but I haven't studied their full capabilities. iTrain appears to be a main competitor of Freiwald. JMRI apparently has automation capabilities, and a lot of people use it. There's also something called RokeRail and CTI. If anybody knows of others that can compare with TrainController, let me know. So back to my situation. Here's the TrainController block diagram for my North Penn branch, with several stub terminals on the left, middle, and right, and the staging yard on the lower right. When I took this screenshot, the red blocks were occupied. We know that because Digitrax BDL-168 occupancy detectors told LocoNet. LocoNet used LocoBuffer USB to tell my computer, which runs TCB. I'm not going to go into how to set up BDLs or LocoBuffer. The manuals are clear. The TCB manual shows you how to configure TCB to speak to LocoNet through LocoBuffer, so I won't go into that either. I'm going to show you how to add momentary contacts to supplement those occupancy detectors and get more precise stopping points. My ultimate goal was, as I said, to get trains to stop at precise points under computer control. When using TCB, there are 5 variables that can affect stopping points: the deceleration settings in the decoder, CV4, the deceleration settings in TrainController Bronze, the train's speed when it enters the block, the constant braking distance setting, if any, in the decoder. Zemo and Lentz have this, ESU and others may also. The Zemo version is especially sophisticated and flexible. Finally, the brake and stop markers you have set up in TCB. Now we're going to handle this by setting brake and stop markers, since they use both occupancy sensors and a momentary contact. Read your TCB manual on how to set up your locomotive's speed, momentum, and braking properties. These interact with the settings in your decoder. This screen shows a bidirectional block with yellow and red triangles, which are the brake and stop markers for each direction of travel. Stub tracks would normally need only one set, pointing toward whichever end has the stop bumper. The locations of the brake and stop points on the display are only approximate and do not necessarily reflect where trains may physically brake or stop. Just because you put the stop marker in the middle of the block, for example, does not mean the train will do that. So in addition to the brake or stop marker, the marker settings in the blue boxes on these slides give you the option to have what they call a ramp. This lets the train proceed some way into the block before braking or stopping. The screenshots show a longer ramp on the left and a shorter one on the right. Unfortunately, the longest ramp was too short for my long terminal tracks. It would stop a slow-moving train too soon before it reached the track bumper. More precise stopping requires another detector of some sort further into the block, which TCB lets you do. TCB could then use the occupancy signal triggered immediately when the train enters the block to slow the train, and then another contact later on in the block to stop the train. This picture from the TCB manual will help explain. This whole section of track could be one block. B1 is an occupancy detector and detects a train located anywhere in the block. B2 and B3 are momentary contacts. The train enters the block and is detected by B1, but only starts to slow down when it triggers B2, and then it stops at B3 before the red signal. In my case, B3 would be unneeded because occupancy detector B1 would slow the train to some threshold speed, and momentary contact B2 would stop it. The speed and braking settings in TCB for the applicable loco would govern the threshold speed. Obviously, you don't want it to be a crawl, more like 15 or 20 miles an hour. There are various ways of doing momentary contacts, like magnetic reed switches, which you can learn all about on the World Wide Web. By the way, to avoid confusion, I'm going to use the term turnouts for the things that Americans call switches and British friends call points. Infrared LED detectors are a perfect technology for this, and they are dirt cheap. There's lots of guidance on the internet telling you about them. Nscale.net has a great website which does that, which I'll include in the description. To show you the relative size, that track in the picture is N-scale, and the detector is just as it comes out of the box with 5mm LEDs. You could use these just as they come for large scales from below the track with the LEDs peeking up through holes in the roadbed, although this placement isn't ideal. Smaller scales or thick roadbed require more creativity. You might find a way to hide the detector in the scenery or a building alongside the track, or replace that big 5mm emitter and receiver with a 3mm pair as shown in the photo. These are also very cheap and appear to be plenty sensitive enough. Don't solder the new ones directly to the board. Attach them via long lead wires for more flexibility in positioning. With long enough lead wires, you can position the emitter and detector across the track from each other. Diagonally works best. Mind the polarity of the LEDs. The picture on the right-hand side shows which leg is which. Connecting them the wrong way around won't hurt the LEDs or detector, they just won't work. With the across-the-track configuration as opposed to under the track, precise positioning is not as crucial, and rolling stock of any color will interrupt the beam. Fiber optics to the rescue. I experimented with using fiber optics to transmit or receive the IR beam. It appeared promising and could actually transmit the infrared beam from the emitter to the receiver, but not well enough for my use. This could merit further experiments. It seems like a lot of people want these IR detectors just to light LEDs, to show the location of trains on a control panel, or operate a crossing gate or other animation, for instance. I wanted the IR detectors to feed information to LocoNet and from there to TCB to run the trains more precisely. The missing link between the IR detector and a TCB or other software is supplied by an optical relay, such as you see on the top left, and a LocoNet device like the Digitrax DS54, 64, or 74. I prefer the 64 because it's easiest to connect, more flexible than the DS-74, much simpler than the DS-54, and can be programmed easily and directly via JMRI, unlike either the DS-54 or 74. The optical relays are available on Amazon, very cheap, 5 for $7. Link in the description. The IR detector feeds a high or low signal to the optical relay, which then can act as a normally open or normally closed switch or auxiliary input for the DS-54 or 64, or as a sensor input for the DS-74. The DS-54, 64, or 74 then tells LocoNet, which tells TCB, which shows if a train has been detected or not. Your devices need power. The IR detector instructions say to use 3 volts DC. The opto relay instructions say to use 5 volts DC. I have used 5 volts for both with no apparent disasters. You may have an old phone charger sitting around that puts out 5 volts DC. Just cut off the plug. I'm not sure if it would have enough wattage, but your mileage may vary. It appears that you must use the same DC source for both detectors and relays. The DS-54, 64, and 74 instructions tell you how to power them. Auxiliary power is optional for this application. The next section will show you how to connect the IR detectors to the relays, and then to the DS-54, 64, or 74, and then to LocoNet. Since the DS-54 has only one female LocoNet jack, daisy chaining it with other LocoNet devices will require one of these 3-way adapters with 1 male and 2 female plugs. Here's how you wire up the detector and relay and their 5-volt power supply. The DS-54, 64, or 74 would be at the top of the drawing. Connections to them are next. The DS-54 uses an old-school 9-pin decoder harness for its 8 inputs. That's 4 aux or auxiliary and 4 switch. Here's how to connect those 9 wires. The COM output of the relay goes to the white common wire of the DS-54. The NO, which means normally open, output of the relay goes to your choice of one of the other 8 colored wires on the DS-54. Note Digitrax does not know how to put things in alphabetical order. Note also the references to control CVs. We will need those later. The DS-64 uses simple screw terminals for its 8 inputs, 4A or aux and 4S or switch, and also for auxiliary power, track power, and a plus common terminal. Here's how to connect them for our use. The COM output of the relay goes to the plus COM terminal of the DS-64. That's the middle one in the group of 5. The normally open output of the relay goes to your choice of aux or switch inputs of the DS-64. Notice how Digitrax has cleverly learned how to put things in alphabetical order. The DS-74 uses a combination of screw terminals for track power, things called P+ and P2+, and outputs for turnout machines or lamps. Then it has a 10-pin header for inputs, designed to use a ribbon cable for easy interfacing to certain Digitrax devices that I don't have. The inputs we care about are the 4 sensor and possibly the 4 switch inputs on the header. Connect the COM terminal of the opto relay to the P+ screw terminal of the DS-74. You may be able to use the P2+ screw terminal or pin 9 or 10 on the header instead, but my way worked. Connect the NO terminal on the relay to one of the sensor inputs on the DS-74. Although the drawing in the instructions seems to suggest the sensor pins are in the top row, I connected the NO terminals of my 4 relays to the 4 right-hand pins in the lower row as seen in the photo on the right. I don't know if that's the best way or the only way, but it worked. I also found it much easier to use those flexi DuPont cables for all those connections instead of bare wires or that unwieldy ribbon connector. Do you have bipolar confusion? Are your highs and lows working backwards? When the IR detector is triggered, the normally open switch on the relay will close, which the DS-54, 64, or 74 recognizes as an aux switch or sensor input depending how it's programmed. When the IR detector sees a train, the DS unit must then tell the LocoNet that the sensor is high, that's HIGH, in order for TCB to understand it correctly. When the detector no longer sees a train, the DS54, 64, or 74 must report the sensor is low. Note, if your IR detector and receiver are across the track from each other, as opposed to under the track, you will likely find LocoNet reporting high and low backwards. To fix that, use the normally closed terminal on the opto relay instead of the normally open. Or move that little jumper on the opto relay, which I put a green box around, move it from one pair of pins to the other pair. You now need to program your DS54, 64, or 74. Here's a little board that I used to test and program a DS54 before putting it on the layout. You don't really need it for the DS64 with its screw terminals and vastly simpler ability to program on the layout using JMRI. Those 3 AA batteries yielding 4.5 volts are just for the detector and opto relay. I used a Euro-style screw terminal block in the middle to connect the relay to the DS54. The wires from the 9-pin connector on the DS54 are very thin stranded decoder wire and hard to capture in such a terminal block. So strip the ends about ½ an inch, bend the back on themselves, and then tin the ends with plenty of solder. They then can be captured firmly in the terminal block. Or you could attach a larger gauge pigtail to each of those 9 skinny wires from the 9-pin connector, which is more elegant. I attached the 9 input wires in the terminal block in logical order, common A, B, C, D, which is not the physical order of the 9-pin connector. It is in this order, A, B, C, and D, that LocoNet identifies the inputs, as you'll see later. Setting the board ID, also known as stationary board address, also known as baseboard address. The first step is to set for the DS54 the stationary board address, for the 64 the board ID, or for the DS74 the baseboard address. These 3 terms appear to mean the same thing, or at least they function the same for our purposes here, but none of the 3 manuals says they are synonymous. This slide is straight from the DS64 manual. Look how easy it is. Not so with the DS54 or 70. So let's program your DS54. Do this on the programming track before you connect it to the layout. You can do it later on the layout, but it's a lot more complicated. Certain inconsistencies in the DS54 manual don't make this any easier. You need to give your DS54 a stationary board address. Don't just use the default address. To set the stationary board address on the DS54, you need to create a thing called a program feedback adapter, which is shown here, which is page 13 of the DS54 manual. Note the manual uses the terms program feedback adapter and program readback adapter interchangeably. They mean the same thing. It turns out you need to also use this to write and read CVs to program the DS54. Figure 7 on page 13 and the text on pages 14 and 26 both refer to a 100 ohm 2-watt resistor. This picture shows the resistor connecting the yellow lead of the cable on output D via the resistor to one of the program track rails. You may have to supply your own resistor if your DS54 didn't come with one. Some sections of the manual say to use the 120 ohm resistor and connect it to the yellow and black leads of one of the output cables. So, with these contradictions in mind, I used a 100 ohm 2-watt resistor and the yellow lead of the output cable plugged into output D, that's the one farthest from the track terminals, and it works fine. After all that preparatory work, page 26 of the DS54 manual tells you the process to set its stationary board address. Follow those instructions reproduced on this slide. For the DS74, go to page 1 of its manual. That's where this slide is reproduced from. In paragraph 5, you will need to choose your own baseboard address. Choose wisely, as we'll see later. This is still pretty easy, but page 6 of the manual gives some diabolically complex instructions on how to use a DT602 series throttle to detect all your DS74s and their addresses and for assuring no conflicts. Make a mental note to thank Digitrax for introducing the DS54 and curse them for superseding it with a far more complicated and less flexible DS74. One arcane point that's not explained well or at all in the manuals is that you have to choose a stationary board address or board ID or baseboard address that will not generate conflicts with other LocoNet devices of the same sort. There's a lot to that, but I think what it means basically is that a DS54, 64, or 74 must not generate LocoNet sensor messages that are the same as the LocoNet sensor messages sent by other DS54, 64, or 74 boards or other LocoNet detection devices. If they do, TrainController Bronze will think that more than one block is occupied when only one really is. You can have sensor addresses and baseboard addresses and board IDs that are the same as your turnout addresses or mobile decoder addresses. If that's not correct, somebody please straighten me out. What address to use? How many are allowed? The DS54 manual says you could have up to 511 stationary board addresses, so I guess 01 to 511 seem allowed. The DS64 manual says the board ID must be between 01 and 256. The DS74 manual does not seem to say how many baseboard addresses are allowed. Whichever DS you have, the board ID or stationary board address or baseboard address will generate a specific set of sensor numbers which TCB can read, as we'll see later. How many detection sections can a DS detector report? With their default settings, the DS54, 64, and 74 will only accept up to 4 aux or sensor inputs that I found usable for detection. On all 3 DS devices, the other 4 inputs are switch inputs which control the outputs, for example, for lamps or turnout machines. But the DS54 and 64 can easily be programmed so that the switch inputs work as aux or sensor inputs instead, giving them the possibility of 8 detection sections. It's not clear from the DS74 manual if that can be so configured. Programming the DS54 via its CVs. Here's the table from the DS54 manual showing what CVs to program so that all of the DS54 aux and switch inputs work as sensor inputs. For aux inputs, CV 33, 35, 37, and 39 all need to be set to 39. For the switch inputs, CV 34, 36, 38, and 40 all need to be set to 23. Here's how to do that using JMRI, and I'll give you those numbers again a little bit later. Pretend your DS54 is a new locomotive with the stationary board address you gave it a few slides ago. You'll need JMRI to read the decoder type. Here are the steps. Using that programming feedback adapter a few slides ago, hook your DS54 to the program track, not your main line. Fire up Decoder Pro. This is the first screen you should see. Click New Loco at the top left. Note I had already programmed DS54 units with addresses 26 and 27, so that's why they appear at the top of the list. If I had not done that, locos 26 and 27 would not appear. Click the button at the bottom right that says Programming Track. That's where Digitrax told you to connect your DS54 to the program track, not the main line. Then click Program. That brings you to this screen. At the bottom of the screen, click Read Type from Decoder. That should bring you to this screen. There, your DS54 should appear in the list. Then at the lower right, click Open Comprehensive Programmer. That should bring you to a screen where you can select CVs using the tab at the top of the screen in the orange box. CV1 is the board or base address in the blue box. For this example, in my test rig, I had already set it to 26, as I described above. For the aux inputs, give CV 33, 35, 37, and 39 a value of 39. For switch inputs, give CV 34, 36, 38, and 40 a value of 23. You will see those values in the red box. Click Write after setting each CV. That's in the green box. If you screw all this up, you can reset the DS54 and start over by setting all the CVs to the factory default values of CV1 equals 1. All others should equal 0. You will also need to reset the stationary board ID to your desired number. Your DS64 and 74 don't have CVs, they have option switches. You can program your DS64 using JMRI on the layout connected to a live LocoNet. If you don't have JMRI, Just use the DS manual to set the option switches. The DS manual clearly says that by closing op switch 13, all inputs are set for sensors. It doesn't say what op switch 15 does, but closing it seemed necessary also, just like you see in the blue boxes here. Closing them is easy. Then click Write Full Sheet in the green box up at the top. At this point, you may want to check your work, and here's where JMRI LocoNet Monitor is a huge help. When the DS54 or 64 is triggered up to LocoNet, track power is on, and you trigger the 8 inputs sequentially, starting with aux A and switch A. This is what LocoNet Monitor shows. In this case, it's a DS54 with board address 26. So those inputs yield sensor numbers 201 through 208, going high when closed, a train is detective, and going low when a train is not detective. If you didn't have LocoNet Monitor, you could derive the sensor numbers by multiplying the board ID by 8 and subtracting 7 to get the first sensor numbers. In this case, 26 times 8 minus 7 equals 201. Those sensor numbers are the data TrainController Browns wants to see. So let's put it on the layout. Here's an overview of one of the terminals and its platform tracks. Each platform track is a single BDL168 occupancy detection block, the border of which is near the top of the picture where the platform track reaches the turnouts at the yard throat. I put IR detectors on 7 platform tracks, beginning with the third one from the front in this picture. That's the track with the Tuscan Red Pennsylvania Railroad coaches. The IR detector in each track is between the ties, about 10 inches from the bumper. The baggage car on track 1 is hiding the IR detectors. You can barely see the detector on track 2 just above it. Test the detectors by running a car or locomotive back and forth over them. You will probably need to paint the underside of the car or locomotive with white or silver paints so it reflects the IR beams. If you hear the relays clicking, the detectors are working. There's a little pot on the detector to adjust sensitivity. If all you want is for the IR detectors to feed LocoNet, then you could probably stop here. But I wanted to interface with controller Bronze and run the trains automatically. To make the detectors talk to TCB, we need to configure the blocks in TCB to accept the LocoNet data to tell the trains where to stop. This gets sort of long, so please hang in there. I'm going to assume you know how to create a TCB track diagram, create blocks, and get to this point, which is called the block editor. The purple box at the top shows we are going to be editing Philadelphia track number 1, which is called block PH01. Block PH01 has one BDL168 occupancy detector, shown in the red box, and one infrared momentary detector, shown in the green box, closer to the bumper. TCB calls these types of detectors contact indicators. We added these contact indicators by clicking the yellow dot in the black box. We can add several contacts to the block if we want. However, adding one momentary contact indicator caused block PH01 to split in 2, hence the white gap between the red and green boxes. TCB calls these contact indicators PH01-1 in the red box and PH01-2 in the green box, respectively, and divides the block PH01 into 2 logical sections or subblocks, even though the occupancy detector at PH01-1 covers the whole block. You could drag and drop the boundaries of these subblocks on the screen to make the demarcation clearer, but that makes no difference to operation. The occupancy detector triggers immediately when the train enters the station track, and the pink bar in the red box will turn red to show PH01-1 as occupied. Once the train triggers the IR detector near the bumper, the pink bar in the green box would then also turn red to show both PH01-1 and PH01-2 as occupied. The occupancy detector at PH01-1 will slow the train, hence the yellow arrow pointing down in the red box. The IR detector at PH01-2 tells the train to stop, hence the red arrow pointing down in the green box. Note we have not created any ramp yet. We may or may not need to do that. Next, we must give TCB data to recognize inputs from the two detectors that go with those subblocks. First, we'll deal with subblock PH01-1. In the digital system box, that's the green box, select LocoNet General, e.g. DS54 and BDL16. Ignore the reference to DS54. TCB will accept our BDL as if it were a BDL16. My BDL for this part of the layout has board ID number 2, so the address for contact indicator PH01-1 is 2, which you insert in the red box. This contact indicator for PH01-1 is fed by the BDL168 input 1, so insert 1 in the blue box. Looking at the LocoNet monitor data at the top of the screen, we can see BDL16 number 2 DS1 highlighted. This confirms our choice of address 1, input 1. Incidentally, because we know the address and input for this BDL, we can ignore the sensor LS figures that are highlighted in yellow in the LocoNet monitor data at the top of the screen. Now let's input the data for subblock PH01-2, the infrared detector. In the green box, select LocoNet generic plain number. TCB makes us pretend our DS54, 64, or 74 is an Ulebrock 63XXX. While BDLs have an address and multiple inputs, DS54s, 64s, and 74s have multiple sensor numbers generated by their board address. To find the sensor number, an easy way is to run a train across the IR detector and see what LocoNet monitor reports. That's the data shown at the top of the slide. We see that sensor LS161 was triggered, so 161 is what we insert in the black box for contact indicator PH01-2. If you don't have LocoNet monitor, you can derive the sensor numbers by multiplying the DS54 or 64 board ID or board address times 8. That's the number of board inputs. Here, the DS54 has board address 21. So 21 times 8 equals 168, which would be the sensor number for the last input, switch D. Subtract 7 and you get 161 for the sensor number, which is the first input, aux A. That's the orange wire on the DS54. The other inputs on the DS54 are then 162 through 168. It's the same process for the DS64, although DS74s are somewhat different. We need a short digression for the new BDL716 occupancy detectors, which have succeeded BDL168s and have a different scheme. You must give your BDL716 a base board address, and its outputs to LocoNet will generate 16 sequential sensor numbers beginning with that address. TCB doesn't need the BDL716 base board address and input number, it just needs sensor numbers. In this example, block PH17-1 has just one contact indicator, which is the first input of a BDL716 with baseboard address 130. When that block is occupied, the highlighted LocoNet monitor at the top of the screen tells us it's sensor LS130 that has been triggered, same as the baseboard address of the BDL716. So once again, we pretend the BDL716 is an Uhlenbrock 63XX generic device, and we insert 130 in the green box. So it's actually rather easy to derive the sensor numbers for BDL716s even without LocoNet. We have now given TCB all the necessary information about our two contact indicators, momentary and occupancy, so we can now roughly set the distances for braking and stopping. In this screenshot, we are editing block PH01. We can see in the red box a vertical blue arrow. A few slides back, this was yellow for braking, but then I clicked on it and it turned blue. Now, if we want, we can use the slider in the brown box to create a braking ramp in block PH01-1, which will be triggered by the occupancy detector. The green box indicates the momentary contact PH01-2, which is closer to the bumpers. As we said before, the ramp in block PH01-1 tells the train to proceed some distance into the block before slowing down, but because we have a second contact in the block, the ramp does not tell the train to stop yet. The relative length of the ramp is described by the slider in the brown box, but that has no actual relation to how many inches or centimeters the train actually would run before slowing or stopping. We probably want a fairly short ramp for terminal tracks so the train doesn't roar down the platform and slow too late. For staging tracks, it may not matter since realistic deceleration may not be a priority. Momentary contact PH01-2 has no ramp because the IR detector is supposed to tell the train to stop right away. The relative location of momentary contact PH01-2 shown on the screen in the green box has no relation to how far it actually is from the bumper. All we can tell is that it's closer to the bumper than the occupancy contact at PH01-2. Also recall that stop just means TCB will reduce the throttle to 0. This does not necessarily stop the train given momentum settings and the other factors I mentioned earlier. At this point, we may want to play with the momentum settings in the decoder or TCB or shorten or lengthen the ramp. Do lots of experimentation. So here's the result. The 8:05 a.m. local from Paoli is running late, so the engineer roars through the yard throat at about 45 miles an hour, only slowing when he reaches the outer end of the platform. TCB reacts as soon as his loco occupies the platform track and slows the train but does not stop it. TCB then issues the stop command when the engine crosses the IR detector between the ties, which is next to that heap of luggage on the platform. Because the engineer had to brake hard, he misjudges and pulls up 10 or 20 yards short of the bumpers. Unhappy passengers have to walk. The engineer gets written up. Now, because this particular loco uses a Zemo decoder, I could fine-tune this by using its constant braking distance function. That way, no matter what its speed when entering the block, the train could be made to stop a set distance from the point where the software reduces the throttle to 0. On the other hand, the 8:30 a.m. express from Bethlehem, pulled by a high-wheeled 440 Camelback, is right on time so the engineer can run through the yard throat at the proper slow speed. When his engine triggers the PH01-1 and PH02 indicators, TCB issues the appropriate brake and then stop commands so the engineer is able to gracefully stop just a few feet short of the bumper. Happy passengers rush to their office, grabbing a coffee and a newspaper. Now, to be fair, not all engines have identical performance, so the best practice would always be to have the same engines using the same platform tracks. And that's about it. To finish up, here's a 1-minute video giving you a flavor of the North Penn Branch Mark II. You'll see the Chestnut Hill area, a bit of the park, and some mainline action. Videography and sound effects by my granddaughter, who was 12 when she made this.